chemical of some kind. In this example, I'm doing salt, but some chemical is coming into the tank. So you can think of, here's the chemical is coming in. In this case, it's salt is coming in, okay? And then it's draining, so you can say it's draining out. Now what you're going to do is you're going to mix the salt solutions coming in, and it mixes with the water here, okay? Now you can have an initial condition, which in this case I said there's 20 kilograms of salt initially in the tank. So the initial condition is going to be 20 kilograms. Okay? We'll have to do some initial conditions with DEQ next time, but we didn't have enough time today. So this is typically what's happening. Now then they tell you the salt is coming in. Now in this case it says brine, which is salt water, of 0.04 kilograms. That should be, I think, kilograms per liter. Yeah. Okay. So per liter, yeah. So they give you the density, so it's 0.04 kilograms per liter. That's coming in, and the solution rate is going to be, what did I say, 20 liters per minute. So the water's flowing in the brine is flowing in at 20 liters per minute. Okay. Now there's two types of mixture problems. This is the easiest type of mixture problem because it's going to drain at the same rate. Okay, so if it's going to drain out at 20 liters per minute, which means what happens to this 10,000 liters during the whole experiment? It just stays the same, right? It's coming in and it's going out at the same rate, right? Now, next time, I think Wednesday, we're going to have situations where it either drains out faster, in which case the water level is going to drop, or it's draining out slower, in which case the level is going to rise. But you need a first order linear for that, and we're going to do that on Wednesday. So for this will be separable. You can do this with a separable DEQ. Okay. I'm going to give you the principle, and then I'm going to ask you to solve it. Okay, so the principle is that we want to know what is the amount of salt in the tank at any time t. So we're going to say Q of t is the kilograms of salt in the tank at time t. Okay? So this function of time is telling you how much salt is in the tank at any time. Because what's happening is salt water is coming in, it's mixing, it's draining, and the amount of salt that's in the tank at any one moment, right, is going to vary over time. So we want to figure this function out. Now we're going to set up a differential equation. And the principle we're going to use is that the rate of change, in other words, Q prime of t, which is dQ dt, which is the rate of change of salt is going to be the rate in minus the rate out. That's the differential equation we're setting up. Now, what is the rate in with respect to salt? How much is the rate of change of salt coming in? What is the rate of change of salt coming in, and how do you figure it out? According to this,
0.04 divided by 20.
0.04
Times 20 liters.
times, right? Because what you're doing is you're taking the density, right, times the fluid rate. So in other words, you've got 0.04 kilograms per liter, and you're multiplying that by 20 liters per minute. That's going to give you kilograms per minute, because you could think of these units as canceling, right? So that's going to give you what? What is this? 0.04 times 20 is what? You should be able to do that in your head.
It's 8.
0.8. Okay. So 0.8. Okay, now, here's the question I'm going to ask you. Well, let me first ask you the easy question. It's going out at the same rate, right? So the fluid rate out is the same. That's 20 liters per minute. But what's the density coming out? That's the question. What's the density coming out? How do you figure that out?
Mass divided by volume.
What is the density coming out? It's the kilograms per liter. What's coming out in terms of kilograms per liter?
0.8 kilograms per unit.
Well, it's not going to be, you're not going to get a nice numerical answer. You got to think. Think of the problem.
It came out like with formula with T.
Okay, something involving T, but what?
20 plus 0.04 T divided by.
Now, because remember, the salt comes in and it mixes with all of these liters that are in here. There's 20 in there. It mixes in with that, and then it mixes throughout that 10,000 liters. Per liter, what is the density of the salt? And what is it represented by? And think about a differential equation, and that'll give you a hint. We're setting up a differential equation, so what is going to be coming out? Q, the function itself, right? Because at time t, there's Q of t kilograms here. And we know there's 10,000 liters, right? So, right, there's the density. Okay, that's where you get the Q. So minus Q over 10,000. Okay, and this is kilograms per liter. Okay, solve the differential equation. Because what you've got is dq dt is equal to 0.8 minus Q over 10,000. Okay, so solve this. And do some algebra. Because it is separable.
Wait, wouldn't it be 20Q?
Oh, and I forgot the 20. Thank you. So let's